Good afternoon. We are back into chemistry again. We have done 12A-1 on the beginning of solutions and solubility. We are moving into 12A-2 now. We're going to be discussing the rate of solutions. We will probably be finishing up this section A today, and from there we will be moving on to section B. But we'll see how much time it takes us to get through section 1 today. Let me start my timer so that I know that we're not running too much on this. Um, so let's start with factors that affect the rate of solution. The rate at which a solute dissolves depends on its solubility, the frequency of collisions with solute particles. Of course, it's the reason why if you break up your sugar cube dissolves faster than if you leave your sugar cube solid. And well, we've talked about a variety of other things, but I mean, that's one of the things we're talking about. Temperature, stirring, the amount of surface area of the solute exposed to the solvent, all is going to affect the frequency of collisions between the particles of the solute and the particles of the solvent. And the frequency of collisions is going to then affect the rate of solution. Again, there's also a discussion of inherent solubility. Uh, I don't know whether or not I can even. Oh, that's not what I meant to do, folks. Sorry about that. Oh, I got it again. Let me try that one. Well, I can move myself off, but you guys understand the word collisions underneath that, right? I don't need to be able to specify there. You're okay with the fact that you can't see the entirety of the word collisions in the middle of all of that. I hope. Um, but I guess whether you are or not, it's going to be the way that we go. Sorry, Mr. Knott's rambling. It's really hard to teach a class to nobody. I mean, and I know you're there, but um, there's no one actually here. So I'm teaching the class to an empty room and hoping that you all watch it. Um, anyway, rate of solution, inherent solubility, number of effective solute solvent collisions. So if we want to change the number of collisions, how do we go about doing that? If you think about that sugar cube in tea example again, number one, how do you get that sugar cube to dissolve faster in your tea? Number one, you can. That's right. You can heat up the tea. If you change the temperature of the tea, if you put the sugar cube down in warm tea instead of the sugar cube down in cold tea, it will dissolve much faster in warm tea than it is going to dissolve in cold tea. You can stir it. Stir. Get your cup and stir. Um, a lot of times we stir things to try to get things to dissolve, and that's common because that's providing that molecular energy, that kinetic energy, to be able to stir the pot so that we have the thing. You can break it up. You beat on that sugar cube until it breaks up into little tiny little pieces. The little tiny little pieces are all going to dissolve a whole lot faster than the sugar cube would dissolve if it wasn't broken up into all those little tiny little pieces. So there's a number of things that you can do that are actually going to affect the rate of solution and changing the number of collisions that's involved there. Temperature. So let's talk about factors that affect solubility. Hold on, I'm going to cough. I promise to put stuff on my hands as soon as I'm done here so that we can. I won't be spreading any germs, although this is not the coronavirus that I'm dealing with. Temperature. Will the solubility of a substance increase or decrease as temperature increases? Let me say that again. Will the solubility of a substance increase or decrease as temperature increases? In general, higher temperatures help solids and liquids to dissolve by increasing the number of particle collisions. So, in general, whenever we're discussing this, an increase in temperature is going to mean an increase in solubility. However, That works very well for liquids and solids. That doesn't work well with gases. What happens if you take your can of Coke, you pour your can of Coke out into a pot, and you heat your can of Coke up? By the way, do you get that? If you pour your can of Coke out into a pot and you heat your can of Coke up, what happens? It goes flat. It goes flat because in the case of gases which are dissolved, or in the case of gases that have dissolved things, there's actually a decrease in solubility whenever there's an increase in temperature. If I increase the temperature to the point um, where I've dissolved certain things in it, the dissolvee is going to escape from the solution. What about pressure? If we're dissolving liquids or solids, whenever we're discussing pressure, pressure has no noticeable effect. You take your material and you put it under pressure. There's no noticeable effect if you're dissolving a liquid or a solid in a liquid. So if I'm dissolving sugar in water, there's not an effect that goes along with dissolving sugar in water if I put it under pressure. Put the water under pressure, I'm not going to get any more sugar that dissolves in it or any less sugar that it dissolves in it as long as I'm dissolving sugar in water. If I'm dissolving alcohol in water, the same thing is true. I'm not getting any more effect from it in this case. However, with gases again are the weirdness that goes along with this. If I increase the pressure, I increase the solubility. This is the reason why when you take your can of Coke and you shake it up and you pop the cap on it, you've decreased the pressure real fast. What happens to the solubility of the carbon dioxide in the Coke? It goes everywhere. Coke just spews all over the place. That effervescence is caused because you have decreased the pressure and therefore decreased the solubility on the Coke. So in this case, dissolving gases actually increase in pressure will increase the solubility of the gas. This brings us to Henry's law. Henry's law states that the solubility of gases is directly proportional to the partial pressure of the gases above the solution. It is expressed as S1 over P1 equals S2 over P2, where S is the solubility of the two different gases and P is the partial pressure above the gas-liquid solution. Of course, it's illustrated by that same illustrated of opening up a bottle of Coke. Hang on. When the 4.5 atmospheres of pressure above the pressure is removed, the solubility of the carbon dioxide in the beverage decreases and the excess gas escapes. This is called effervescence. It's the rapid escape of a gas from a liquid gas solution. Well, folks, that is the end of 12A-2 today. And I think we're just going to stop there today. It's already 4 o'clock whenever I'm recording this message, and I still have history to do. So I think we're going to stop with 12A-2. You will have a quiz coming up. I will get you the Quizlet up for that, as well as get everything else up for that you're going to need to get up for that. So just making sure that all of that is ready for you. I'm actually recording this on Tuesday. You'll be watching it on Wednesday, and the quiz will be on Thursday. So just so you're aware of how that is all going to go down. Thanks. We appreciate it. It has been fun. This is really weird, and I'm looking forward to getting back to seeing my class again soon. If you have any questions, you know where to find me. Thanks. Bye.